In this video, we're going to continue with our example of applying the ANOVA procedure to answering our research question. And so we pick up here in the next step of calculating what's called the sum of squares. And there are three unique sum of square values to calculate when we use this type of ANOVA procedure where there's only one factor and there are more than two independent groups of data. The first one is referred to as the sum of squares within, and this is calculated by adding up all of the deviations, rather the squared deviations, between a single score and the average of the group within which that score was obtained. So for example, this could be the score of just one of the basketball players in that first group. The X bar group is the average for that particular group. And so this calculation would be carried out for all of the participants in the study. So the deviations from the basketball group would amount to 7 unique deviation calculations. Moving to the second group, which are the football players, the X would be the score for the first football player, and X bar would be the average for the entire group of football players. So each deviation score would yield would have to be squared, and then all of those squared deviations would be added up, and that gives us what we call the sum of squares within term. If with our example, it's important to note that we would have 35 of these squared deviation terms to add up. The next important sum of squares value is the between sum of squares, and the between sum of squares takes the same idea in that it's based on a deviation score. The only question is what is the deviation score we're calculating. So that deviation score is where we take the average of one group and we subtract the average of the overall for all groups, the grand mean. So in this scenario, we would end up with 5 deviation scores, and each of those deviation scores would be squared. So because we have only 5 groups, so we would add up all 5 scores, and then we would multiply it by a correction factor, and that's the number of cases per group. And so in our example, the number of cases or participants in each group would be 7. The total sum of squares is calculated two different ways. It's calculated by taking a single score and subtracting the grand mean and then squaring that. So in this case, we would have 35 squared deviation scores, but as opposed to the sum of squares within, where each score was subtracted by its respective group average, in this case, each score is subtracted by the grand mean. And then we add all of those up to give the total. The second way to calculate the sum of squares total is much quicker, where we would just simply take the sum of squares within value and add it to the sum of squares between value, giving us our sum of squares total, and that's what has to be reported when we complete our ANOVA procedure. So in order to move forward, what we eventually do with those data or those calculations is we calculate what's called the mean square between. Recall that the mean square is another term for the variance, and this refers to the variance that exists between the group averages. And we calculate that by taking our sum of squares between and we divide it by the degrees of freedom between. We then have to calculate the variance, or mean square within, that represents the inherent variability that exists inside the groups. And that's where we take the sum of squares within and divide it by the associated degrees of freedom within term. Now, the way those are calculated in this particular type of ANOVA is that the degrees of freedom between is equal to k minus 1, where k is the symbol that represents the number of groups. The degrees of freedom within is calculated by taking the total sample size, all the participants, subtract the number of groups, so n minus k, and the degrees of freedom total is calculated by the total sample size subtract 1. Now that these data will be used to calculate our two variance terms. And once we calculate our two variance terms, we can then determine our F obtained. And the F obtained is the test statistic based upon the data. And so when we take a look at the mean square within, sometimes this is referred to as the mean square error term. And in subsequent different types of ANOVA, the mean square error term is one that will be used consistently. This denominator value indicates the variability that would occur by chance alone. So the variance within is not determined by any systematic difference that's inherent to each group. That is captured by the mean square between. So the denominator term here, the mean square within, is that variance not accounted for by any unique group differences. Now, once we calculate our F obtained, our test statistic, we have to compare that to some threshold F value, and this is where we use our ANOVA table, also referred to as the F table. And so the F table is used to calculate that threshold or critical value. We don't need the data collected from the participants, but what we do need is the family-wise or overall type 1 error rate, and unless stated otherwise, we typically assign that to an alpha level of 0.05. And the second item that we need is the sample size and the number of groups, and then once we know the overall sample size and the number of groups, we can calculate the degrees of freedom as outlined on slide number 12. So the way we read this table is we start along the top row, and the top row is the row indicating the degrees of freedom for the numerator. And so that's the degrees of freedom for the between variance. And our value is 4 because our degrees of freedom for the between is a number of groups k minus 1. We had 5 groups, subtract 1 gives us a 4. We then go to the far left hand column and we look up our degrees of freedom for the denominator, and this subscript indicates error, but I use the term within in this context, so I'm using those terms interchangeably. So recall that this is to calculate that degrees of freedom. It's an n, uppercase N, for the total sample size minus k. We had 35 total participants minus 5 groups, and that gives us 30. And we find on the table where those two intersect. They intersect at a value of 2.69. That's our critical threshold value to evaluate the F value from our data. So on this slide, here we're going to take a look at the actual numerical values. So I used Microsoft Excel to calculate the sum of squares. And so I calculated a sum of square between of 50.82. I used the within. I used Excel to calculate the within of 47.37, and I added up the total of the between and within to get 98.19. The degrees of freedom, which I covered on the previous slide, but we'll just go through this step by step. The between term is a k minus 1, so that's our base formula. We know we have 5 groups minus 1, that gives us a degree of freedom of 4. Our within term is our total sample size. Remember, we had 5 groups with 7 participants in each group, so 5 times 7 is 35. We minus the 5 groups, and that gives us 30, and we needed that on slide 13 to look up the critical F value. and then we calculate the degrees of freedom total as an n minus 1. Our total sample size is 35 minus 1 gives us a 34. But also note here, we could have calculated the total degrees of freedom by just simply adding the between and the within. 30 plus 4 gives us 34. So that gives us another method to confirm if our calculations for the degrees of freedom total was correct. So that ends this video on part 3 for the ANOVA calculation.